Good morning. Welcome back. So today we're going to be doing kind of a combo lesson. We're going to do 7.6 and 7.7, basically the A part. So a lot of intro to something really cool called an exponential function. You're thinking, why? Why more? Why do I have to learn more? Well, I have this little sentence out here for us. Let's check it out. So, exponential functions are used to model populations. Like, what the heck does that mean? So maybe there are 10,000 elephants left on the planet, and we know their population is decreasing by 4% each year. How many elephants will be left in 7 years? That's important to know, right? Because we don't want more animals to become extinct. Or maybe we have a population of just random, a beetle, like a little bug. And that sucker is exponentially growing, kind of like that little green Japanese beetle. And that one just wipes out trees and fruit, and it's a little herbivore that loves to eat everything. But that is not a native beetle to this area, but it can wipe out plants. So maybe we're going to model that population. So maybe there's 100,000 of those beetles, and they're growing by a rate of 20% each year. Well, then how many beetles will there be in 5 years in this area? That's important. Or even if you're someone like I'm a cat lady and I love my cats and I've adopted all 7 of my cats. I'm now down to not 7 at one time. I'm not that crazy. That's 7 cats over the last, how old am I? 52. So the last 30 years or so. Okay. I have 3 cats right now. But the population of feral cats, aka stray cats that are out there, might be growing or decreasing in a certain area. Maybe we want to study why, right? So that's one area of why we study this thing called exponential functions. Carbon date artifacts. Maybe they find this really cool clay pot in a cave somewhere, and they want to know, well, where the heck is this? How old is this clay pot? Well, one of the ways they can date that is through carbon dating, and that is an exponential function. Kind of cool, right? Also, it can help coroners determine the time of death. So they take the temperature of the person, and then they can use an exponential function to determine what time did they pass away, because that might be important. Compute investments. Maybe you're going to be an investment person, or just like me, I invest my money in different little things, and I can compute if that money is going to go up or if it's going to go down over time, and by how much, right? Bacteria size over time, you know? So there's this bacteria that's growing by 2% each minute. How big will this bacteria be in 8 minutes? You're like, yikes, that's a yucky bacteria. Yeah, it's growing. As well as a lot of other applications. This particular lesson today, we're going to study exponential growth, exponential decay, and this one not until the next time we meet. So it's compound interest, where our money in the bank grows exponentially, so quickly, or more quickly than a linear function. So today our focus is on exponential growth and decay, how to identify exponential growth and decay, what the heck does an exponential function look like? Maybe what does a graph look like? And again, today's just the intro day, so I'm not trying to stress myself out. I'm not trying to stress my students out. I'm just trying to be nice, calm, and cool about a really fun topic. Kind of a cool topic. Nerd. Yep, that's me. Okay, so the first thing I'm going to start off with is just plain old notes. If you want to get a clean piece of paper out at home, that would be swell, okay? So let's talk about what the heck does an exponential function look like? Well, you guys know what a linear function looks like, right? Y equals mx plus b. That's our linear function. This pen is not very dark. So maybe I'm going to turn off this so we can do some great notes and that won't get in our way. So a linear function, we've had a lot of experience with. A linear function is y equals mx. Do you remember what m is? Do you remember? Starts with S. Slope, right? Tells me how my line leans. And then b, my starting point. Particularly, it's my y-intercept. It's the starting point where it crosses on that y-axis. And that axis is the one that goes up and down, okay? So we've already studied this one. This is a linear function. We had a whole chapter on linear functions, but that's not what we're studying today. So, but that's one that we've seen before. So let's talk about, well, what the heck does an exponential function look like? Well, let's check it out. So please take some notes. Cool. Exponential function. And let me get maybe a better pen. Trying to find the one that's nice and dark. Ooh, here we go. There you go, my friends. That is what an exponential function looks like. Sometimes you might see it written like this. Same thing, lo mismo. It's exactly the same thing. Instead of a dot, they use parentheses to indicate product or multiplication. No difference at all. Well, you're like, well, what do all these parts mean? Well, y equals would be whatever the answer is to whatever's over here. So let's discuss what these parts mean. Each part has a name, and each part tells me something different, okay? So I'm gonna look at the top one. I'll use different colors too, might as well. The A piece of the formula is the initial value. You can think of it as the initial amount. So how many beetles did we have to start with in that example that I gave you? Or how many bacteria do we have that we're starting with? Or how much money are we placing in the bank? Or what were some of the other ones? Population. How many people live in that city to start with? So this is that start value, that initial value. Where do we start number-wise? Cool. Let me grab a different color. And let's hope this looks pretty. The B is my growth or decay factor. Growth means how much it's increasing above 100%, or decay, how much it's decreasing below 100%. And then we have this beauty little queen right here. Let me use a different color. This is, it seems like it's usually a time, like how many years are we talking about? So that elephant example that I gave you. So there were, I think, 10,000 elephants and they're decreasing by a certain amount. How many elephants will there be in 7 years? So that would be the time factor right here. It could also be like my husband plays poker. He's a poker professional. He loves to play poker. So sometimes you start off with 1,000 people in a tournament, and each round a certain amount of people are cut when you get down to one table of poker players, right? So this might be the number of rounds of poker they are playing, the number of sessions of poker they are playing. So this is our initial bit, okay? So we're, again, covering exponential functions. There should be an S there. That formula looks like y equals a times bx. The a is the starting value of whatever it is that we're talking about, and b is the growth or decay factor, and x is my time. So I'm going to stop the video here. So this was just a really nice little intro, and then video 2 we'll be getting into the nitty-gritty. Okay? Thanks. Bye.